Merapi is one of the world's most active volcanoes and very dangerous. More than 700,000 people live around Merapi. For them, it's a real risk. Evacuation takes place at level 4, danger. Merapi is famous for its pyroclastic flows, its lava streams. And suddenly, the mountain of fire erupts. Merapi, Indonesia's most active volcano. Streams of lava measuring up to 800 degrees Celsius surge into the valley. Silent, insidious, deadly. Lava chunks shatter in gigantic clouds of glowing ash. In 2010, villages were impacted that had previously been safe. The lava flows took a new direction. The old Javanese capital, Yogyakarta, was at risk. For 6 weeks, the volcano hurled red-hot chunks of lava 17 kilometers into the valleys. Once again, it was clear why scientists have rated Merapi a high-risk volcano. During this eruption alone, more than 350 people were killed. In Indonesian, Merapi means mountain of fire. Volcanologists rate it as one of the 10 most dangerous volcanoes in the world. It's capable of erupting so dramatically that the consequences would be global. 25 kilometers to the south, Yogyakarta lay on the main axis of the 2010 eruption. Previously, the lava had flowed westwards, and residents had abandoned that area long ago. How can scientists assess the risks from such an unpredictable volcano better? The island of Java, with its population of 160 million, lies on the Sunda Arc, the most active volcanic region in the world. Here, the Indian and Australian plates are subducting under the Pacific plate, only a few centimeters each year, but with dramatic effect. Indonesia is famous for its very big eruptions, for instance, the Toba eruption about 75,000 years ago. It almost destroyed the whole of humanity. With the help of geosatellites like the Tandem X mission, deformations are visible from outer space. They can provide evidence of dangerous tectonic shifts. The data is analyzed in laboratories such as the Geosciences Research Center in Potsdam. For more than 20 years, scientists here have been studying this high-risk volcano. Only recently have they detected in satellite pictures a deformation running right through the mountain. Radar data shows how a crack 250 meters long has formed in the volcanic plug after a sudden eruption. This crack lies in exactly the same direction as an old fracture zone. If that one becomes active again, it could have wide-reaching consequences for volcanic activity in central Java, and explain why Merapi's eruptions have suddenly changed direction. To obtain more precise information, the scientists are planning an expedition up to the crater's edge.
If we start to go late in the morning, we cannot really see which are the most active part or what are the features. So for the infrared measurement, I really prefer to have nighttime images.
Maybe we should simply spend the night. Look here on the map. Somewhere here. And then we'd only have to walk up this path early in the morning to look into the crater. Merapi's twin volcano, Merbabu, has been dormant for 300 years. But now scientists have measured seismic activity here as well. Volcanoes are common throughout the region. Scientists have discovered that they are linked deep underground. Merapi is the most active. It usually erupts every 7 years, sometimes more frequently. The eruptions are generally signaled by growth in the lava dome. A lava plug composed of very thick magma solidified on the surface. It has been pressed out of the vent by the pressure inside. This plug can arch over the sides of the volcano like a dome until it shatters. Time-lapse photography of a very similar volcano, St. Helens in North America, shows how lava domes grow and collapse again. Some of them coincide with very frequent pyroclastic flows, as in the case of Merapi. Big eruptions are generally preceded by increased tremors for days in advance. That's why the volcano observatory set up by the Indonesian Geological Service in Yogyakarta is connected to a number of seismic stations around Merapi. Tectonic earthquakes and ones that indicate volcanic activity are recorded here around the clock.
Itu menjadi masalah utama dalam
Our most important task is to see when the population must be evacuated.
Masyarakat harus dievakuasi. Ya.
For this, we have a system of 4 warning levels. There's normal activity,
Normal, waspada,
followed by alert, increased alert,
awas,
and danger.
Menggunakan berbagai.
We employ various observation methods, and the results are analyzed here in the office.
Kantor ini bertugas untuk
It's our job to pass on this information to the regional government.
Melalui pemerintah daerah setempat.
For Thomas Walter from the German Geosciences Research Center in Potsdam, the Indonesian Observatory is also an important resource. It provides him with valuable data about seismic activity and possible deformations on Mount Merapi.
Wir haben verschiedene Ziele.
We have various aims. On the one hand, we want to understand the changes in Merapi better. That's a geological issue. In the past 3 or 4 years, Merapi has been providing a very different picture. For instance, we know about previous eruptions caused by tectonic earthquakes. And so it's very important to understand whether the current situation on Mount Merapi is controlled by an entirely new kind of, possibly reactivated tectonic zone or weak zone. That's the geoscientific question. But of course, there are also technical aspects. We want to develop new technical methods and test them. Methods we've developed in Germany are put to the test here for the first time, to see whether they can be applied to active volcanoes. 5:30 in the morning. They set off on the first leg of the expedition. Their destination? A far-flung observation post in the immediate danger zone of Mount Merapi. The journey takes them through villages declared high-risk areas since the last disaster. This road also provides the only escape down the valley. The road ends some 4 kilometers from the crater. Exclusion zone. From here, the scientists want to measure the gaping fracture on the southern mountainside from a safe distance. It's too dangerous to climb the mountainside itself. They are trying to find out whether this crack really influenced the pattern of volcanic activity. In recent months, there have been 4 quite large explosions here, without any warning. This was unprecedented at Mount Merapi. The volcano now appears to be reacting even to changes in weather.
Diese Explosionen ereigneten sich nach
These explosions occur after heavy rain, and we rather assume that they are what are called phreatic eruptions. That is to say, by water penetrating the hot magmatic body. It tries to expand but can't, so it escapes in an explosion of steam. That is a really new situation here at Mount Merapi. The observation hut serves members of the volcanology service during periods of increased activity. The German scientists are now using it as a gauging station. With a 3D laser scanner, they want to obtain precise images of the topography of the volcanic crack and the lava dome. Instruments like this are mostly used by architects and civil engineers to identify damage to a building. Using this scanner on a volcano is something new. The scientists are looking for data that would reveal cracks and changes in the structure of Mount Merapi. The laser scanner is supposed to produce a very precise topographical elevation model to measure the crack in its depth, so that we can calculate the depth to which rainwater can penetrate and where this interaction between an older magma body and water is taking place. We combine that with infrared measurements, which give us information about the temperature in the crack. So here we are looking directly onto the crack. Later we'll see it once again from the summit, and then we can better assess the interaction that is actually taking place. Weather keeps interrupting the research. A new position, cloudy skies. We are heavily dependent on weather conditions whenever we go into the field, external conditions over which we have no control. We can only reduce the frequencies here to 30 kilohertz, and that's insufficient to penetrate the clouds. We try to adapt as far as possible. That's why we get up at 4 in the morning and start scanning as early as possible. We have the best chance of good visibility in the early hours. At a distance of 4 kilometers, the measurements don't provide any clear indication of the lava dome's real shape. The scientists have to ascend to the crater's edge. Nevertheless, these 3D scans of the volcanic cone are very valuable.
We get a better image of this dome and the volcano edifice up there. So if I want to use this data that we get here only once, it will be used in the numerical models that we will be running to infer the sources which run the whole process up there. But if we can make another scan, maybe in 1 month or 2 months, something like that, then we can use this second image that we get and compare it to the first one that we already have. Then we will see the deformation that has been undergoing in this time interval. So, yeah, as you know, later on we will use this deformation to better image the sources which drive this process.
The break in the volcanic cone reaches right down into the valley. Within just a few years, a yawning canyon, up to 250 meters deep, has opened up along an old tectonic crack, the Valley of Gendol. During major eruptions, hundreds of pyroclastic streams, bombs of lava rock and pyroclastic flows hurtle down here, the most dangerous spot at the foot of Mount Merapi. Nevertheless, gangs of workmen come into the natural quarry. If the volcano suddenly erupted, they'd have no chance of escape. Valuable building material, gravel, earth, lava rock, is exposed by the force of the volcano. On the edge of the Valley of Gendol lie deserted villages, ruins, covered in just a few years by lush vegetation. The hot ash clouds that swept over the edge of the Valley of Gendol in late October 2010 only brushed this village. Nevertheless, they burned to the ground everything in their path. 26 residents were killed. It now lies in the exclusion zone, but life is slowly returning. Close to the volcanic cone, on a spot that has so far proved safe, the German geophysicist Birger Gottfried Löhr has had a bunker built. It lies 5 meters below the surface and wouldn't give much protection in the event of an ash flow. It has another purpose. By means of a broadband seismometer and undisturbed by traffic vibrations, Löhr is able to receive signals from the depths of the Earth. He measures earthquakes within some 600 kilometers of the Earth's surface. Together with many other seismometers in the region, Löhr has been able to register the increase in quakes at a depth of 100 kilometers. The earthquakes follow a pattern that corresponds exactly to the collision zone between sinking crusts and the Pacific Plate. By measuring the tiny differences in speed between seismic waves, the scientists were also able to identify the rising paths of the liquids that ultimately form the magma from Mount Merapi. It's mainly water from the sinking plate that penetrates the upper layers. As it passes through the Earth's hot mantle, chemical reactions occur with the solid rock. Magma, a thick, hot slurry of rock, is only formed at a shallow level. These discoveries contradict previous assumptions about the driving forces of volcanoes. We especially wanted to find the magma paths and where the magma is stored. We all know the image from children's books of a cone-shaped, bladder-shaped magma chamber underground. And when I started here, we also had this idea of a bladder that lay 4 or 5 kilometers deep. However, scientists did not find a cone-shaped magma chamber under Merapi, or indeed under any other volcanoes. They began to doubt the truth of the current hypothesis. If there's no magma chamber here, where is it? French scientists, such as the volcanologist François Beaudoucel, are also involved in a long-term project searching for the reservoir of the highly active Mount Merapi. We've installed 45 seismic stations here, which enable us to get close to the magma and produce a precise image of its layers. We've also installed stations on the top of the crater where the eruption occurred in 2010. Of course, we are interested in the processes and forces that drive the magma upwards from the reservoir so that it causes an eruption. The size of magma reservoirs can be an important factor in estimating the destructive potential of future eruptions. One of the few methods of identifying these storage sites in the Earth is still the precise analysis of earthquakes and their speed delays. We have two aims. First, we're researching basic scientific ideas. We're trying to understand this kind of volcano. And the better we understand this system, the better we can help the Indonesians. That is the second aim, to predict the risk more accurately so that people can be evacuated in time. It's about saving lives.
De mieux comprendre les systèmes volcaniques et donc d'aider les Indonésiens à faire des évacuations et à sauver des vies.
Although scientists have been studying Mount Merapi for more than 70 years, their research has been slow to influence life in the shadow of the mountain. Many Javanese are deeply religious and trust in good mountain spirits to protect their lives. It's true that humans cannot control volcanic eruptions. On that point, the scientists have to agree with the people who live here. Masts have been erected around Merapi with surveillance cameras to observe the volcano. Thomas Walter wants to install some more cameras to close the gaps in this monitoring system. Climbing the 40-meter mast is not a job for the faint-hearted. A colleague from the Volcano Observatory offers to perform this dangerous operation. When visibility is good, a camera like this can contribute a little to the system of disaster protection. And it gives the scientists from Potsdam, in faraway Germany, direct access to current data. At the moment, we're working on ways of being able to process the data in real time. For instance, by defining various categories, distinguishing an eruption from a cloud, and recording movements in the dome on the summit. That's deformation data on which we can base geophysical research. Series of photos from the cameras are especially useful for showing how lava movements develop. That enables scientists to estimate, for instance, the mass that is moving and to forecast future cracks in the dome. Total camera surveillance also provides another benefit. Roads, bridges, and river valleys are closely observed. That means that the destructive force of the dreaded mud flows, called lahars, can be estimated immediately. Lahars often occur during active phases when volcanic ash combines with heavy rains. They form suddenly. Usually one has only a few minutes warning, and then only when a lahar is spotted somewhere. When Merapi erupts, the destructive slurry sometimes flows right into the center of Yogyakarta. More than 600,000 people live in the city, where only a few suburbs have so far been declared danger zones. Officials say it's impossible to evacuate Yogyakarta. The Sultanate, with its Gadjah Mada University, is an important spiritual center in Indonesia. Its residents don't only live in the shadow of Merapi, this is also one of Java's most active earthquake zones. In 2006, a disastrous quake killed more than 5,700 people in the region. Part of Indonesia's largest Hindu temple, Prambanan, also collapsed. As an immediate result of those tremors, an eruption of Mount Merapi, which was occurring at the same time, increased threefold in strength. The scientists working on the edge of the crater also have to consider the danger of a sudden earthquake. Before starting their climb, they check once again for any signs of possible volcanic activity. I assume that it's quiet at the moment. None of the instruments show anything unusual. However, that can change quickly. We're in contact with the observatory. That's important, because early indications of change, which we call precursors, are sometimes very late in occurring. That means changes can occur within a few hours or even minutes. And that's important to communicate, which is why we keep radio contact with the observatory around the clock.
Und deswegen sind wir bei unserer Expedition auch rund die Uhr im Funkkontakt mit hier dem Observatorium.
The north side of Merapi. From here, the only path providing access to the summit. The scientists have to climb 1,300 meters to reach a plateau, where they will spend the night. They hire a dozen Indonesian bearers to transport technical equipment and food.
This you can, and this is heavy, most heavy.
For everybody, it's an adventure with an uncertain outcome. They don't just have to climb 3,000 meters. They will be entering an area in which there's no protection from sudden, explosive eruptions. The weather begins to turn. Clouds descend onto the summit. When the expedition reaches 2,000 meters, the vegetation becomes thinner. The group of scientists with less to carry arrives more quickly via an old crater's edge. They still have 1,000 meters to climb before they reach the summit. The peak is shrouded in mist. And this doesn't just reduce visibility, it also muffles sound, so that they'd not be able to hear falling rock as they climbed in the cloud. Half an hour later, the group of bearers also looms up out of the mist. At the base of the summit is a geological station belonging to the Volcano Observatory. It was completely destroyed during the last eruption. A short distance away is a small plateau, the Pasar Bubra. It is strewn with chunks of lava rock. This is where the scientists want to set up their base camp for one night. It would be dangerous to stay any longer. The arduous climb takes its toll. They need another 10 hours to reach the summit on the north side. They also urgently need good weather to carry out their research at the crater. You can perhaps vaguely make out in the distance how steep the mountainside is at this point. Those are Merapi's old volcanic domes, and this area here hasn't been covered by new lava streams for a long time, mainly by very explosive eruptions, which are very rare. Here, between us and the summit area, there are also some larger chunks which offer protection, and this area has proved relatively safe. This is certainly no spot for a camping holiday. The local people tell me that they usually only come this far and no further unless absolutely necessary. One definitely shouldn't spend too much time on the summit, and we'll keep it to a minimum tomorrow. They check their equipment before the final ascent. Using a simple camera drone, they want to photograph the crater from above. That should provide them with 360-degree images of the lava dome, from which they can deduce its condition and volume. However, the upward current is not very strong. Besides, they don't know how the quadricopter will react to the thermals in the crater.
At least it's flying.
The conditions are unfavorable. We have poor visibility, so we can't steer the drone very well from a distance or see what position it's in. As a backup in case of strong thermals, the scientists are relying on a helium balloon. It has proved its worth on previous expeditions in Chile and on Kamchatka. It can also be used for flying a camera over the crater. However, the gas cylinders are much too heavy to carry up onto the crater, so the balloon is inflated at the base camp. The heavy cloud has lifted without them even noticing. Rapid changes in weather are common up here. For a short while, the Pasar Bubra Plateau becomes visible, before fading into the brief sunset. 3 members of the expedition have climbed down again to the valleys to gather firewood. Even this close to the equator, the temperature drops to 5 degrees Celsius at night. They plan to set out for the summit in the middle of the night, to be able to start work on the crater's edge before dawn. At 2:07, the seismic instruments at the Žraka observation station register unusual movements. They are coming directly from the Pasar Bubra Plateau. Then the Indonesian observation post sounds the all clear. The minor tremors were probably caused by humans in the vicinity of the geological station. It was the members of the expedition who started their ascent to the summit shortly after 2 o'clock. The hardest part lies ahead. Loose scree from cooled chunks of lava. In the dark, they can hardly see how steep it is. They can only feel it. The group must stay as close together as possible. Any stragglers could be struck by loosened chunks of rock. The balloon group can hardly keep up. The balloon may be light, but it's incredibly awkward to maneuver up the steep mountainside. Just over an hour later, they catch their first glimpse of the valley. To the south, the city of Yogyakarta, above which Mount Merapi soars forbiddingly. Shortly afterwards, they arrive at the crater's edge. The scientists start setting up their instruments.
I
think conditions are ideal. We've got incredible visibility. In the distance, you can see first light. I think in half an hour the sun will rise. You see Yogyakarta, the city. The sea of light surrounding this mountain is incredible. That's all residential area. And the conditions are very good for gauging. There's a slight wind. It's still a bit too northerly. Ideally, it will turn so that we can float the balloon over the crater. The infrared expert has to begin his temperature gauging before sunrise. Only then is the data useful, when it's not influenced by sunlight. He makes a photo series comprising hundreds of images. Later, when put together, they will provide a very precise idea of the lava dome's temperature. The new crack is clearly visible. That's where rainwater penetrates the dome, causing dangerous gas explosions. Whereas the surface is really cold, the body of the volcano is permeated with hot zones. In daylight, the huge dimensions of the crater become visible. It's 400 meters in diameter. Half of that is the lava dome, which rises 80 meters above the bottom of the crater. A mixture comprising mainly steam and sulfur thrusts upwards from a depth of several kilometers and escapes through the crack. At sunrise, the scientists start their fieldwork on the dangerously narrow rim. To climb down into the crater itself is out of the question. Nobody knows how stable the lava dome currently is. The laser scanner is brought into position. The whole team has been waiting for this moment with bated breath. The scanner measures a cloud comprising some 5 million individual points, each with its exact three-dimensional position. Never before has the surface structure of a volcanic crater been recorded with this degree of precision. The scientists are especially interested in the structures of the lava dome. At what points is the dangerous plug unstable? Where is there a threat of new eruptions? The scanner appears to be recording usable data. It is providing an exact, measurable view into the crack, to a depth of some 40 meters. Ideally, one would of course return several times with the scanner that we have here, every 6 months or once a year. It depends on the activity and the changes to the dome. But we can also do quite a lot with just one scan. We can measure the directions and cracks, the depths and structures, and what parts of them are potentially unstable. Or perhaps how this crack will develop, where it will open up more, and in what direction.
Yeah. Michaela, let it go, please. Let it go, let it go. I cannot hold it this way.
During the morning, the wind increases. 20 knots, wind force 5. The head of the expedition decides in favor of the helium balloon instead of the drone. The combination of kite and balloon is especially designed to keep steady even in a gale. Well, that's the theory anyway. Cameras are attached to the lower wing. They're supposed to capture a bird's-eye view of the crater. But the wind keeps forcing the balloon in the wrong direction. It's hard to control and not be swept along with it.
Und mit der Schlaufe geht noch, oder?
Ja, das Anstrengendste ist gar nicht ihn zu halten, sondern den Karabiner.
There's also poor visibility. Nevertheless, after more than 1,000 shots, the images are what they're looking for. This is the first complete look into the crater since the lava dome cracked. Together with the laser scans and infrared images, these photos will provide the scientists with an extremely valuable image of the lava dome system.
Das generelle Wachstum von Lavadomen.
The general growth of lava domes is already quite well known and understood. What we don't understand is how lava domes collapse. The prevailing wisdom is that a lava dome occurs as the result of thick magma and that the sides break away as the result of new magma covering it. But Merapi is a good case in point, which shows that it's a lot more complicated, where, for instance, external influences such as changes in weather, strong rainfall, or tectonic earthquakes also lead to the breaking of lava domes. And that's the difficulty with this kind of lava dome. For instance, a combination of lava dome fracturing with what we call ash flows and then earthquakes can't be forecast, because earthquakes, for instance, can't be predicted. So there's a need for more research to try and assess that kind of combination in advance.
Derartige Kopplung besser auch im Vorfeld schon abzuschätzen.
The balloon can only be recovered about midday. The scientists have been on their feet for 12 hours. They hope to reach the valley again in the late afternoon. Actually, everything went well. We've gathered data, and that's what it's about. The wind was rather strong, and the balloon is a combination of balloon and kite. We could hardly keep hold of it. Well, we did keep hold of it, but the problem was getting it down again. The drone is very complementary to this helikite. The helikite is more stable when it's windy. It's a pity that the winds are so strong. A drone is okay in winds of up to about 15 knots. Here they are much stronger. We would simply lose the drone, so we didn't even try to use it.
We are coming down now.
It will take months before the data has all been analyzed. But in Potsdam, even the provisional results indicate that the expedition has been successful. If this bit here is actually a small crater and becomes unstable because of the crack, it's part of the dome that's at risk. Well, the valley is open here down to the left. Right, and here we have... And here a bit has slipped, broken away. And frankly, I see these two shadow areas. There is definitely a hole there. It could be an explosion crater.
Aber es kann sein, dass da wirklich ein Explosionskrater ist. I think it's more like an explosion crater.
Yeah, like this one, because you don't see the accumulation of the material. So if this was just a lateral collapse, you would see an area where this material is accumulated. But apparently it's been removed everything, so it's more explosive there.
Also so die Möglichkeit, einen Dom in
We were never able to observe a dome breaking up, and as far as I know, nobody in the world has been able to do that. But because we examined it shortly after a large eruption and possibly before another one, this is very valuable data. If this is an unstable structure, we'll have to see with infrared gauging if there are temperature changes here. Usually that would indicate that there's a weak zone there.
Yeah, this is the most hot, or the hottest part at the time of the survey. And here, this white color, this very bright color, represents high temperature. I measured above 150 Celsius at the time of the survey.
So this hot temperature, this is exactly at the place where we think another fracture has formed.
Yeah.
Also das Interessante ist,
what's really interesting is that the dome itself is really cold, and a cold dome gets blocked up or ultimately forms a plug in the volcano. The danger, of course, is that it's blown off in new eruptions. The research doesn't only produce snapshots of the most dangerous part of the volcano, it also clearly shows that observing the lava dome plays a pivotal role in assessing the risk. However, one key question about Merapi has not been answered. How much magma lies hidden in the depths? In other words, how much more dangerous can this volcano become? Very little usable data rises to the surface, gases and steam from the deep layers. The magma chamber that scientists have long been searching for under Mount Merapi appears not to exist. Instead, the analysis of comprehensive data indicates an anomaly, a zone that dramatically differs from the normal state of the Earth's crust.
In
an extensive experiment, we constructed 120 stations in central Java and measured earthquake waves. We then analyzed this data and discovered, to our surprise, a zone in the Earth's crust that shows very greatly reduced, extraordinarily greatly reduced, seismic speeds. That is to say, the speed of the earthquake waves is very greatly reduced in this zone. Everything that is red here, covering the whole of central Java, a volume of some 50,000 cubic kilometers. It's the biggest volcanic reservoir ever found. A gigantic zone, reaching 40 kilometers into the Earth. The volcanoes, including Merapi, are sited in this area. Contrary to previous notions of magma chambers, there's no bladder here. Fluids rise, causing the rock to melt and resulting in distinct layers in the crust. This completely new model is confirmed by other volcanoes. Whether the anomaly becomes greater or smaller, we can't say. We would have to repeat the experiment. From surveys in Kamchatka, we know that these anomalies change in combination with eruptions. After an eruption, they are very weak. But before the next eruption, they build up again and become relatively strong. Here in central Java, scientists are confronted with a puzzle they can't yet solve. The fact that it's bubbling under the surface at various points is clearly visible. Steaming fumaroles, mud pots, are only one indication of the danger that could be lurking here underground, comparable to what scientists call supervolcanoes, which could destroy life on Earth. Yellowstone is always mentioned. In South America, there are some similar big reservoirs, magma reservoirs, in the depths. But the volume that has been observed here at Merapi is even greater than those. Is Merapi on the way to becoming a supervolcano, whose eruption could have disastrous consequences for the whole world? That's extremely hard for scientists to predict. We don't know if Merapi will eventually become a supervolcano. We have lots of data about volcanoes in general, but very little information about how an active volcano becomes a supervolcano. We know, for instance, very little about the size of the magma reservoir and the processes that occur there. The mountain of fire, at the foot of which people have lived for generations, farming, raising animals. This mountain was only comprehensible in the past to people who understood the spirits. Humans made contracts with them for the volcano to leave them in peace. Even today, they are extraordinarily casual about the risk posed by living in the shadow of Mount Merapi. Three harvests each year, the ancestors who are buried here, a good climate. Those are all good arguments that persuade many residents to remain. I come here as a scientist, and I don't impose my ethical norms and demand that people clear out. That's not for me to say. There's an information chain, a warning chain. But I wouldn't destroy those spirits and mystical models that have developed as empirical models over the centuries without being able to replace them with something better We have to be convincing as scientists. And the process of convincing people is evident here. The people increasingly take us and our statements seriously and incorporate them.
Mit unseren Äußerungen wahrgenommen werden und dass das eingebaut wird.
After the last big eruption, it was possible to rescue hundreds of thousands of people from the ash cloud. That has improved the status of the scientists among locals. In the Volcano Observatory, there is regular discussion between scientists and the emergency services. The geoscientists from Germany also pass on their results to the Indonesians after every survey expedition. These are often just small pieces in the puzzle, but they can help understand the mountain and its dangers better. New research techniques such as laser scanning could in the future regularly be used to predict the danger of gas explosions and pyroclastic flows more accurately.
So in the perfect case, you would want to walk all the way around to the other side of the crater, scan from there, combine both of the scans and have a full view. But of course that is very difficult in the field.
Kerjasama dengan para ahli.
Working together with scientists from abroad is very important, whether it occurs at quiet times or in crises, because it's very hard for me, for us here, to really predict Merapi's activity.
Memprediksi aktivitas Gunung Merapi.
A massive eruption with global consequences. That scenario is quite feasible at Mount Merapi. But in spite of all the research, the question of when and whether it will happen is one of the secrets that the mountain of fire still refuses to yield.